Hey, welcome to the Explainer. Today, we're cracking open a fundamental tool in data science, linear regression. It might sound a little technical, but it's really the secret engine behind everything from forecasting house prices to predicting sales. And trust me, by the end of this, you're going to get exactly how it works. So let's just start with a huge question. How can we possibly look at the information we have right now and use it to make a solid guess about something we don't know yet? Whether that's figuring out what a house will sell for or how many products will move next quarter. How do we do that? Well, believe it or not, the answer starts with something we all learned back in math class, a simple, straight line. Seriously, that's it. That's the secret weapon we're going to dive into today. So here's our game plan. We're going to break down what linear regression actually is. We'll start simple with just one predictor, and then we'll power it up with many predictors. After that, we'll look at how it finds the so-called best fit line. And finally, we'll learn how to actually read the results. All right, first up, what is this thing really? At its heart, you can just think of linear regression as a kind of statistical detective. Its whole job is to find and measure the relationships that are hiding inside your data. So here's the deal. It takes this big, messy cloud of data points and draws the one single straight line that makes the most sense going right through the middle of them. This line describes the relationship between the thing you're trying to predict. We call that the dependent variable because it depends on other stuff, and the information you're using to predict it, which we call the independent variables. Okay, let's ease into this. We're going to start super simple with what's called, you guessed it, simple linear regression. This is where we use just one piece of information to try and predict one outcome. So picture this. Let's say we want to predict a person's weight, but the only thing we know about them is their height. Now, it's not going to be perfect, obviously, but you can see how there's a relationship there, right? Taller people generally weigh more.
Now, every straight line in the world can be described by a really simple equation, and this is the one that powers the whole thing. I promise it's not as scary as it looks. We're going to break down what each little piece does. The formula is just y equals a plus b times x.
So let's tackle those letters. Y is our unknown. It's the thing we're trying to predict. In our example, that's weight. X is the piece of information we already have, our predictor. In this case, that's height. That's it. Y is what you want to know. X is what you already know. All right, what about that B? That's the slope. You could think of this as the engine of the whole equation. It answers the most important question. For every 1 inch increase in height, how many pounds do we expect the weight to go up? It tells us how steep the line is, which really tells us how strong that relationship is. And that just leaves A, the intercept. This is just the starting point for our line. It's the predicted value of y if x were 0. So in our example, it's the predicted weight of a person who is 0 inches tall, which I know makes zero sense in the real world, but mathematically, it's the anchor that locks our line into place. Okay, so predicting with one variable is a great start, but let's be honest, the real world is messy. It's rarely that simple. So to get more accurate, we need to bring in more information, and this brings us to multiple linear regression. I mean, think about it. Height alone isn't going to give you a perfect prediction of somebody's weight, is it? Age, lifestyle, diet. There's so much more to the story. We usually need more data to make a good call. A classic example is trying to predict the price of a house. You'd never just use the square footage, right? Of course not. You'd want to know how many rooms it has. Maybe you'd have some kind of score for the location, the age of the house. All of these are predictors. And that's the whole idea behind multiple linear regression. It's the same exact concept, but on steroids. Instead of just 1x, we're throwing a bunch of them into the mix. Each one adds a new dimension to our analysis, and the model weighs all of them at once to come up with the best possible prediction. Okay, so this brings up a really important question. If you have all these data points scattered on a graph, you could draw an infinite number of lines through them. So how in the world does the computer figure out which one is the single best one? The goal is actually pretty simple. Just make the mistakes as small as possible. What the computer does is it measures the distance from every single one of your data points straight up or down to the line. The best fit line is the one that makes the grand total of all those distances, all those errors, as tiny as it can possibly be. It's the line that kind of hugs the data the closest.
Okay, but there's a catch. For this to actually work and give you results you can trust, your data has to play by a few rules. We call these assumptions. Think of them as a quick quality check. Linearity just means a straight line is actually a good way to describe your data. Independence means your data points aren't influencing each other. Homoscedasticity, and that is a mouthful, just means the errors are random and consistent. And normality means those errors don't have some weird hidden pattern.
All right, so we've built the model, the computer did its thing, it found the best line. Now what? This is the fun part. What is it actually telling us? How do we read the dashboard? Well, one of the first numbers you'll look at is called R². The easiest way to think about it is like a report card for your model. It's a score between 0 and 1 that tells you how much of the story your predictors are actually explaining. So, for instance, let's say our model spits out an R² value of 0.75. What on earth does that tell us? Well, it's telling us that a solid 75% of the reason why house prices go up or down, in our example, can be explained by our predictors: the area, the number of rooms, and the location. That other 25%, that's caused by other things we didn't include in our model. It's a really simple way to see how good of a job our model is doing. And that, right there, is the magic of this whole thing. Linear regression gives us a powerful way to go from just staring at a bunch of numbers to actually understanding them. It lets us turn a messy cloud of raw information into a clear, insightful line that tells a story. So from now on, when you see two things that seem connected, whether it's years of experience and salary or study time and test scores, think about that straight line that might be hiding in the data. Now that you know how to find it, what kind of relationships are you going to start discovering in the world all around you?